So welcome, to my talk. So what I will talk about in this, in the next 15 to 20 minutes is how the recent advances in ORCA 6, make it possible that we now are able to treat more and more real-world systems, and what that means we will see on the next slides. My name is Christoph Riplinger, so I'm Managing Director, co-founder of FACTS. FACTS is an abbreviation for Fast and Accurate Computational Chemistry Tools. And we are a spin-off of the Max Planck Society, the MPI for Kohlenforschung, and our mission is to bring these fast and accurate computational chemistry tools that are developed in academia to bring them to industry. So we are essentially ORCA's link to industry. And just to give you an overview, who is behind ORCA? And I just want to show a few people here also. So ORCA is mainly developed on the academic side by Frank and his team. There's a few dozen really smart, talented people working on developing all kinds of new features. And the FACTS team, we are a company. We are also based nearby, so where the MPI is located, and we are now almost 20 people, and we are working closely together with our industry partners. And in order to make ORCA smoother, make it easier usable, and we are also working on other tools, and we are also working in quite a few collaboration projects together with our industry partners. And besides that, there is also a large network of academic collaborators that are all contributing to ORCA. And all this manpower has led in the last years to tremendous growth in ORCA usage and in popularity of ORCA. And so we are measuring each year the popularity of ORCA by counting the number of citations to the respective to the software papers, so to the reference papers. And what you can see here is the citation count over the last years, and you can see that we have a kind of exponential growth. So we are growing at above 25%. So actually, we just did the numbers for last year, and now we had a strong increase of more than 30% last year. And it is also reflected in the numbers that we have in the forums. We have almost 80,000 registered users right now. And you might be interested in we are working with industry, so who is working with us on the industry side. So who are the people who make use of quantum chemistry in industry? And that's a lot of pharma companies. We have a lot of big pharma companies. We can't show everybody due to legal reasons, but we can show a few of those. And also biotech companies, technology companies, chemical industry, material science. So it's a broad range. As much usage as we see in academia from all different kinds of areas, we have the same also in industry. And also there we have expert users, but we also have lab users who are using our tools. Now let's come to real-world chemistry applications. So what do I mean here? So for us, one important aspect is as you might imagine, is protein-ligand complexes, but also on the process chemistry side, we are a lot looking at reaction complexes. So these are important systems for us, for our customers, and of course also for a lot of.
You have the same as system, or you can select it.
Yeah, no.
Is there a problem? Or I can hear. Hello?
I think Petra's just was unmuted by accident.
Okay, good. Then other aspects could be also supramolecular complexes, and sometimes it also might be interesting to use microsorbation approaches to sorbate explicitly certain solutes. And so if you are looking at these types of applications, then there's a few aspects that are important. So you want to, if you have accurate results, you don't want to wait long. So you want to have these results faster. And you want to, like we saw with these proteins, for example, you want to treat larger and larger systems. And this also helps you you want to treat the environment. So that might be a solvent, or that might be, if you are in a solid state, it might also be the matrix that is in the surrounding of your actual molecule of interest. Also, of course, a molecule is present if you are doing an experiment at room temperature, for example. And then the conformational space of that molecule is also important. So modeling low energy conformers, or if you think about reactions, also modeling low energy complexes how are reactants, how are they approaching each other, or how do metal ligand complexes look like? So all these are important questions. And of course, if we do chemistry, if we do reactions, then also we want to understand how is the mechanism of a reaction. And so all we want to. I will give you a short overview on how our recent advances make all these steps here, all these aspects, make them better. And so one aspect is efficiency. Frank already showed us a slide on the speed up of ORCA, so I don't want to waste too much time here. I just want to emphasize what that means for you in practical terms. So if people in 20 years ago took a system like this and it took them using an at that time state-of-the-art QM package on an at that time state-of-the-art computer, and they waited for about a month for the result. And nowadays, with a new ORCA and a new hardware, such a calculation is just taking half an hour. So that's showing you how large of a speed up we have in that time, what is possible by now. And just to give you a few examples, so this is a regular drug-like molecule, and you can run, these are single point energy calculation timings. You can run these calculations in a few seconds, such a calculation. Or if you go to couple cluster theory, so we have the DLP-no approximation, then you're just waiting a few minutes for a calculation like this. You can also go to larger systems like 500 atoms, and such a calculation on a very decent density functional level of theory just takes about an hour. And now, as Frank said, we can run huge calculations like proteins here. This is a much smaller protein than what Frank showed before, but such a calculation just takes a few hours on modern hardware. Now, this is just the efficiency part. So now, what is important when we treat systems in a realistic environment is often solvation. And so here we have quite a few advances compared to previous ORCA versions. So we used to have CPCM and SMD models in ORCA, and they are very powerful. But also, if we look at more properties in solution, then there's other approaches that give us like better results. And so here we have two implicit solvation models, which we added now with ORCA 6. So that's the Draco SMD model, which is coming from Stefan Grimmer and group, our collaborators there. And also we work together with Simon Müller and his group on a new implementation of Cosmor S for ORCA. So now these two features are available with ORCA 6, and using those features, you can get much better solvation-free energies and other solvation-related properties. Sometimes it's important to not just model solvation implicitly, but sometimes you need microsolvation. What does that mean? Sometimes you need to have explicit solvation molecules in your model that are binding to certain functional groups, and these, if you include those into your model, then the results of your simulation are much better. And so we have now also a solvator, an explicit solvator available within ORCA, which gives you, for example, or can give you much better spectroscopy results, or also better solvation properties. And I want to show one example here. This is the simulation of a VCD spectrum. So here on the VCD helps us to distinguish between different stereochemistries, and VCD is also known that it is very sensitive towards solvation, and that sometimes it is important to include explicit solvent molecules into the simulation to get a good, decent agreement with the experimental results. And that's what we visualize here. So we have this molecule, and we have once run the calculation only with an implicit solvent molecule, and you see an overlay of the experimental spectrum together with the simulated spectrum, and it's not too good. And now if we include just a simple single solvent water molecule, then you see that the agreement becomes much better. And with ORCA 6, we try to provide you with a tool which, in a black box fashion, enables you to run these simulations. Now, another aspect that is important. So we have treated now solvation as an environmental effect. Another aspect that is important is the conformational sampling, and not just for single molecules, but also for larger species. So if we have aggregates of multiple molecules. And so here we have now the Docker available within ORCA, which gives us the possibility to, which takes a lot of burden from your side. So previously you needed to put these molecules together in a manual way using a graphical user interface. And now with ORCA Docker, Bernardo will talk more about this later. We give you tools so that you can automatically put those systems together and put them together in a most favorable, most probable way. This is for assembling non-covalent structures, but also, of course, for single molecules. The conformational sampling is a very important aspect. And in the next talk, which is starting in a few minutes, Bernardo will talk more about all these topics. But these are, just want to emphasize, these are very important to treat real-life chemistry. Now, what I will talk a little bit more about is reactions and how you can use ORCA to model reactions. Two aspects. Sometimes you want to elucidate a reaction mechanism, and sometimes you also want to understand how does a molecule react with certain compounds. And so let's have a look at the first problem. If you want to elucidate a reaction mechanism, then you have a reactant, and you also know what a product is. And so what we have within ORCA is the so-called NEBTS method, which is a combination of the nudged elastic band method, where you put together a reactant and product complex. These are found here on two minima of this potential energy surface. And then what the NEB method does, it finds the minimum energy pathway on that potential energy surface. So it gives us a very good minimum energy path, and it also gives us a very good initial guess for the transition state. And then in the next step in this NEBTS method in ORCA, we do a quasi-Newton transition state optimization, which gives us a very reliable structure of the transition state. It's just a short depiction or visualization of how it looks like. So we try to minimize the energy of the path between both to get to the minimum energy path, and then last we optimize to the transition state. And so we published that method. We of course benchmarked it also, and here what we used were two popular benchmark sets from Zimmermann and Schlegel, and they were quite diverse. So there's a lot of different reactions in these test sets, and what we found that we had 100% success rate, and that showed that this method can be used as in a black box session. Also, after implementing this, publishing the paper, we also were curious, okay, we wanted to challenge our method further. And so we asked around in the academic community, and we asked our collaborators, can you give us examples that are really very, very hard? And so what we found was this one example here. That's an iron 3 peroxide catalase reaction. And you can see that there's 4 bonds that are in total that are formed or broken. And we were told that elucidating this reaction mechanism took them like about 2-3 months and a lot of computing resources, a lot of 2-dimensional scans and so on. And what we did was we used the NEBTS method, and we just gave it the starting structures like for reactants and products, and it ran through in less than a day without any need for user intervention. And so that's just one additional example where it shows how good you can use this for real-life catalysis research. Another aspect is also enzyme catalysis, and so that's what I show here on the right side. So we have within ORCA available a QMMM model, and this QMMM model is of course also interfaced and integrated with the NEBTS method. And what you can see here is that we can also simulate the minimum energy path of a reaction and also get to the transition state of a reaction within the protein. So here we use not full DFT for the entire system, but we use a QMMM type approach. And what you can see here is that here we just show all the atoms without defining which is the level of theory we use. But you can see that we get the minimum energy paths. You see that here we have a 3-membered ring, which is opened up in this reaction. There's a 5-membered ring that is formed. And you can see that the enzyme is doing what it's supposed to do. It's stabilizing this transition state by in this case, providing protons here. So there's a proton coming from the tyrosine, and there's another proton being accepted by this aspartate. I want to emphasize that now we have a very robust way to get transition states with ORCA, and now with the GOAT, which is what Bernardo will show us later, we also can run not just conformational searches on the minima of systems, but also even on the transition states of, on transition state structure. So sometimes you might be interested in what are the different conformational states of a transition state. So that's when you want to elucidate reaction mechanisms. Another important aspect can be that you want to know about the stability of your compound. So for this, we have in ORCA 6 now available, the so-called GOAT react feature. So as I said, Bernardo will talk more about GOAT. Here, I just want to emphasize that GOAT is a reaction exploration tool. So we don't just look at conformers, but also at different possible, at the entire reactomer of the compound. And an example you can see here. So we have a molecule and we have oxygen. And what GOAT does, it gives you possible reaction outcomes, possible products. And here you can use all the tools that are available within ORCA, use GOAT to run a conformational search, use a Docker to put them together, and use GOAT React to get to these different reaction outcomes. And that can help you, for example, to also find the weak spots of a drug. And here I'm showing another example that we are in the course of publishing. Also, this is the photodegradation of, or this is about the photodegradation of diazepam by singlet oxygen. So that is one mechanism of photodegradation. So oxygen is excited, and then this very very harsh oxygen it can attack molecules. And what you can see here is the outcome of GOAT React. That's different reaction outcomes, and you see that we sort them here by their thermodynamics. And of course, if a reaction is supposed to take place, then the thermodynamics needs to be favorable, but also the transition, the activation barrier needs to be low enough so that the reaction is accessible. And then when you combine this together with the NABTS method, then you can see that, for example, this is a potential reaction outcome because it has a favorable thermodynamics and it also has an accessible transition state. Now, talking about environmental effects, so proteins are very important for us. I didn't talk about that. There's a few examples that I could show you. Just want to also highlight that we have the method, the LED method, the local energy decomposition method available within ORCA, where you can model the interactions between drugs and proteins. So the interaction of the drug with the active site residues. But here I want to refer you to Giovanni Bistoni's talk, who's talking later today about energy decomposition methods within ORCA. I want to thank you for your attention. I want to thank our partners who were very much involved in creating all these and developing all these nice features. And thank you for listening.